All right. Um, Hello, everyone. Welcome to week one Common Misconceptions. This is going to be a weekly video that the production company, the 170 production company, will be producing. Um, the goal of this is to sort of answer any common misconceptions or questions they might have from topics over sort of this week and the previous week. As you may know, Piazza has a lot of Q&A features, and so if you have questions, feel free to ask them there. But we're hoping to sort of collect a lot of the common ones into a video for you guys if anyone prefers sort of staring at our faces instead. um, all right, take it away, Avi.
Yeah,
Yeah,
thanks so
thanks
much,
so much,
Tim.
Tim.
Oh, do you hear that echo? Did you hear that echo?
I did not hear the echo.
Okay, it was there for like a second. Okay, never mind, never mind. I'll cut this out of the video. Um, yeah, James, thanks so much. Let's dive right in. So the first question that was asked on Piazza that a lot of people upvoted was uncertainty about which grows faster. So does log n raised to the power of a or n to the b for different constants of a and b grow faster? And I was a bit confused about that. I would love if you could explain that right now.
Yeah. So Avi, as I understand it, the question is log of uh, let's say n to the b, is this like uh, O of n to the a? Let's say for like a and b greater than 0.
Yep.
Yeah, so surprisingly, this is actually true for all a and b greater than 0. Maybe this sort of makes sense. Let's say if a and b are 1, right? We probably intuitively understand that log n is big O of n, right? As in log n grows slower than or equal to n asymptotically. But like one thing that might be confusing is like, what if b is like 10? Like what if it's log n to the 10th? And what if it's like square root of a? Sorry, square root of n, excuse me. Yeah, so it turns out that this is still true, sort of for all a and b. And like one way we can see that like briefly is if we just rewrite each of these two functions as exponentials. So this is a nice trick that maybe you may or not have seen before. So this log n to the b, we can write as like 2 to the log of this quantity, right? And here it's going to be log n to the b. And then quantity here, n to the a, we can write as 2 of log n to the a, right? It's just like exponentiating and logging again, right? And then using some log rules, we can get this to look like 2 to the b log n. And we can get this to look like 2 to the a log n. So this is like sort of just pulling down powers, if you will, inside the logs. Sorry, let me, just to be clear, this is like a log here, and yeah, that's the log of that. Yeah, and then you can see here, maybe, we know that a log n, oh, sorry, that's big. A log n grows faster than b log n. And so therefore, 2 to the a log n will also grow faster than 2 to the b log n. Actually, if you sort of use this exponential trick, you can apply the limit rule and go from here to verify yourself, but I'll sort of leave it at that and leave it for you guys to check.
Awesome.
Does that make sense, Avi?
Yeah, that did. Thanks so much, James. I actually have a follow-up question about Big O. And I think I'm confused about why or is the limit definition of Big O, is it an if and only if implication? I don't understand if it goes back and forth or not. Could you explain that one time?
Yeah, great question, Avi. This is like something that confuses students every semester. At least I imagine. I've been here that many semesters. But yeah, here we said, oh, if we want to show that log n is big O of n to the a, sorry, log n to the b is big O of n to the a, then we can use the limit rule, right? In particular, the limit rule implies big O, but it's not necessarily true that big O always requires the limit rule to hold, right? So let's like see an example of that. We can maybe briefly understand why that's not the case. Yeah. So maybe one as like a brief segue, let's like take a visual of like what it means for one function to be big O of another. Like in some sense, it just means like there's some multiple of the function. Let's say this is c times f of n, or I'll use g. And like f of n sort of always lies below this, no matter what it is. Right? Yeah, so like, let's take a look at an example, right? This is sort of separate. This is like sort of intuitively how you might think of big O notation. Yeah, so let's take a look at an example. So what if we take f to be, let's say, or let's use n to be consistent, like 1 plus sine of n. You probably won't see this. Like this may be like some really weird example, but let's say f of n is 1 plus sine of n. Then what does that look like? You know, the runtime as n goes to infinity kind of looks like this. Well, we kind of intuitively feel that the runtime here is O of 1, but maybe like the limit rule doesn't apply because, well, actually, like here the limit rule doesn't apply because you know, this function is sinusoidal, right? It never reaches like one particular value, and so it won't have a limit. But we can see that it's contained by like the line n equals 2, or g of n equals 2. And so in particular, that implies that f of n is O of 1. Yeah, so like in general, the takeaway here is like maybe for functions that like don't have nice limits or like aren't really smooth in the sense that like you can take a limit, yeah, like you might want to use other tricks instead.
Got it.
Or here the definition of the big O.
Love that, James. Thank you. Thank you so much for that. So another common big O misconception that I've been hearing is that, you know, when you talk about g of n is equal to theta of a function, so theta of f of n, for example, does that mean that g of n here is actually equal or approximately equal to a constant multiple of f of n? Or like, could you explain what theta here means? Is it like a bound? Is it a multiple? I'm a bit confused about that.
Yeah, so like theta means that like it's sort of for f of n to be theta of g of n. Let's go up to this picture up here. It means that like it's bounded above and below by some constant multiple of g of n, right? But crucially, it doesn't actually have to be the same constant, right? So this could be like a different constant. Let's say like c1, or let's say call this c2 and call this c1. So this is c2 times g of n, and this is f of n, right? So these don't, like you can see here, f of n might not be approximately equal to like any particular constant multiple of g of n, but it's sort of bounded by these two, right? To give like maybe a more concrete example for anyone who wants to check it later, it's like you can consider f of n to be like 2n plus, let's say, n sine of n, right? So this thing, maybe you can see it already, is this thing is going to be bounded above by 3n, right? Because this is always less than or equal to 1, this sine n term. And it's also going to be bounded below by n, because this thing is, this term here is going to be greater than or equal to -1. So here you can see that the constants here are different. In other words, like it's not exactly equal to like some constant multiple. It's just sort of sandwiched between maybe two different constants.
Got it. Got it. No, that was super helpful. So I kind of want to move on now. Or actually, sorry, one more big O misconception on my mind is that if I have kind of this function, you know, f is equal to O of g, does that hold for all h such that when my function g is O of h, then f is equal to O of h? Essentially, is one implying the other? If f is equal to big O of n, does that give us f of O of n squared for free?
Yeah, that's a good question. It does, and it kind of falls out of the definition of big O. Like intuitively, Avi, maybe you might think about it as like F being O of G means that like F sort of grows asymptotically slower than G, right? And G being O of H means G grows asymptotically slower than H. So then you'd expect at least that F would also grow asymptotically slower than H, or slower than or equal to, right? And indeed, we can check this. Actually, I think we can sort of, I'll outline it real briefly. So what does it mean for F to be O of G? This means that there's some C such that like F of N is less than or equal to C times G of N for, some N, like past some N. And then what does it mean for G to be O of H? It means there exists some, let's call it D, such that G is less than or equal to D times H of N past some N. In particular, what we can imply, or what we can see from this is that F is less than or equal to C times G of N, which is less than D times H of N. So F is less than C times D times H of N. Sort of just substituting in this expression here for G. And in particular, this implies that F is O of H. Hopefully that like lines up with what you'd naturally expect. Does that make sense, Avi?
Yeah, that does. That does. So I kind of want to move from Big O now, and I'm curious about, in lecture, I understand that Professor Vazirani discussed this whole idea of the Master Theorem and this tree that expands and grows as, more work gets done, and you have all these different layers. I don't understand the intuition behind the ratio. So we had this, A, B, and D variables, and there's these formulas that Master Theorem states based on like the relation between D, B, and A. But at a high level overview, can you explain the intuition behind why that makes sense? Like why Master Theorem even makes sense in the first place?
Yeah, that's a great question, Avi. So let's remind ourselves of the notation. So here A is the branching factor, which is like sort of how many subproblems we create. B is like how much we reduce the size of each subproblem by from sort of its parent problem. So let's say like reduction factor of subproblems. And then D is just like the sort of power of our polynomial of how much work we're doing at each layer, right? So if the size of the subproblem is n, then we do n to the d work. Okay. Yeah, so let's like maybe give some intuition for why there's like these three different cases in the Master Theorem. It sort of boils down to like how quickly we're creating subproblems, like how much work we're creating at each level versus like how much work we just did at the current level, right? One way you might think of this is like if we create like half as much work at each level as in sort of compared to like the level above, then the amount of work is going to be just like mostly done at the first level, right? And that would be if A is less than B to the D, right? What that means is that like sort of the number of times that we've branched into small subproblems is less than sort of the reduction that we're doing in like the problem size of the subproblems. Feel free to like go back and read over the textbook or like lecture to like review this. And I think Avi actually talked about this in the mini lecture. But hopefully like this gives some idea for like the intuition behind it. You should think of it as like in one case, in this case right here, like the rate at which we're creating subproblems is less than the rate at which we're sort of like reducing their size. And so most of the work is going to be done at the first level. So this is like And then like if A is equal to B to the D, then will be like sort of all the work is done equally, right? We're branching just as much as we like reduce problems, and then equal work on layers. And then finally, if A is sort of greater than B to the D, then that means that we're branching faster, then we're sort of reducing the size of our subproblems, and so most of the work is going to be done at the bottom. And then like the next step sort of beyond that is just doing some algebra to see, like if most of the work is done at the top, what does that mean for asymptotic rate?
Love that, James. Really appreciate that answer. I think that clears up a lot of like the intuition behind Master Theorem as well. In my last kind of final questions that I want to ask, I know there's like this find the valley problem that we discussed sometime in lecture homework, and I'm confused how find the valley runs in logarithmic time, because it seems like you need to look at least every element, since any element could be the valley, and I just that didn't make sense. So I'd love if you could explain how that's log time.
Yeah, so the key here is like at every step, we can rule out half of the array from like sort of being a possible candidate for the valley, right? Let's say I look at the middle of the array and I see that it's sort of decreasing, then I know that the valley can't be to the left of the middle, right? If like the middle element is greater than the middle element minus one, sorry, middle element plus one, then the sort of left half of the array has to be all decreasing, right? So it's impossible for the valley to be contained there. So we can actually rule all that out. And similar argument can be made if we see the middle element is less than the middle element plus one. This is like, maybe you can compare it to binary search. With binary search, we can rule out half the array based on like whether our comparison is greater than or less than, our median is greater than or less than the element that we want. And that's exactly the logic here. There is like, cases where you do have to check through every element of the array. Like, let's say if you're looking for like the max of an unsorted array, every element could be the max. And in particular, you actually have to look at every single element to make sure that it's not the max. But here, we're sort of exploiting some structure in the fact that it's like sort of decreasing and increasing to avoid checking every element. Hopefully that kind of like makes some sense on like, helps you get some idea of when you can use the argument of like, you have to look at all the elements and when you can sort of expect a log time algorithm.
No, I really appreciate that. Thank you. For my final question for today, I was going through the homework and I was doing the median of medians problem. And I don't think I understand the intuition between how the median of medians problem actually works. So is your end result the median of medians, or are we trying to find the median of the kth smallest element? And I guess like if you could just explain that a bit clearer, just like, help me understand that, that'd be amazing.
Yeah, that's a great question. So the algorithm that actually finds the kth smallest element, we call it quick select. And their variant that uses median of medians is called better quick select. This is at least what we called it in the discussion. The role of median of medians in this algorithm is to pick a good pivot for quick select. So if you recall, sort of in the naive quick select, we pick the pivot randomly, right? And we found that maybe this is bad because we can end up picking pivots that are close to the max or the min. So we end up like splitting, our partition of the array doesn't like help us that much. Maybe it partitions off like one or two elements. The useful thing with median of medians is that you can guarantee that you're partitioning off, let's say 30% of the array. You'll actually prove this in the discussion, or you can have a look at the solutions if you haven't done it yet. And this is like at the cost of doing some extra work. In order to find this good pivot, we have to do a little bit of extra work, but we can check using like by using induction on the recurrence relation, we can check that this is still like okay and actually is good for our overall runtime. But you can look at either the walkthrough video or the solutions for more details on that.
Thank you, James. I really appreciate this Q&A session. For anyone watching, I hope this is helpful in clarifying some doubts from James. James, any final thoughts?
Happy to be here. Thanks, Avi.
Awesome. Thanks so much, everyone. And again, always, if you want the Q&A, the production, like the 170 production company to answer your questions, feel free to add us in Piazza, or if you have common misconceptions that you want our Q&A videos to cover, just let us know in Piazza or tell your live discussion TAs, and we'll produce those videos for you on these every Thursday, every week. So thanks so much for listening, and we'll catch you in a future video by the 170 production company team. Thanks so much.